for the titration at different points. And so when we set up a titration, we're going to add different amounts of base. This is a typical titration. We could also titrate a base with acid, that is, put acid in the burette rather than base. And so in this example that we have 25.0 milliliters of hydrochloric acid, and this was at 0.100 molar. And then we're going to titrate this with varying amounts. We'll just call it, maybe we'll call it Y, since X is your usual change. So I'll call it Y milliliters of sodium hydroxide. This is at 0.100 molar. And so the typical points in the titration are, we could get these points quite quickly from the curve. And so if we look at the curve, this is 0.100, this is 0.100, so we'll need an equal amount. And so at 25 milliliters, we should have the equivalence point here. And then at 12.5 milliliters, we call this the half equivalence point. And so this is an equivalence point. This is a half equivalence point. And we could get any other fraction. So for example, if we want the 1/4 equivalence point, that would come at 6.25 milliliters, the 1/4. The 3/4 equivalence point, that would come at 18.75 milliliters. The 1.5 equivalence point, would be another, it would be 37.5. And so we'd have the 1.5 equivalence point up here. Y milliliters. It's variable. And so in a typical titration problem like this, we'll do a number of calculations, not just one. But what we want to do is we want to get enough calculations to kind of map out what the curve looks like. And so at the 0 point, we just have acid. And so if we have 0.100 molar HCl, then I don't think Kw would be a significant contributor to this. And so this is going to start at pH 1. But what happens if we go to the half equivalence point? How much does the pH climb by? And so we could do that calculation pretty quick. So let's go ahead and do some of these calculations now. So the first calculation we'll do is the half equivalence point. The original calculation was just the 0.100 molar HCl. And I ignored Kw and just got the pH from the power of the concentration there. -1 becomes +1. How many sig figs is that? This is 3 sig figs here. I only have 2 sig figs here, so I need 3 sig figs. So the initial pH should be 1,000. Anything preceding the decimal is not significant. Anything after the decimal is significant. So let's take a look at so we could do the 1/4 equivalence point too. And just have equivalence point for right now. So at the half equivalence point, then we're adding 12.5 milliliters. So plus 12.5 milliliters. You could do it either millimoles. If we do millimoles, I'll take 12.5 times 0.9. It gives me 1.25 millimoles. Then at the end, we convert it. Or we could do it concentrations. Concentrations seems like a bit more of a hassle than millimoles, but I like it myself, so I do concentrations instead. And so what I do here is we need step I, which would be the solution dilution. And so I have my original 25.0 milliliters of cell solution. And then I'm going to add to this 12.5 milliliters of the silicon dioxide solution. So altogether, I'm going to have 37.5 milliliters. And what I have to do here is just figure out what new concentrations are going to be. So for the HCl, we would look at the dilution here, which is going to be, I think we already did this, 25.0 over 37.5 of 0.100 molar. And that came out to, I think it came out to 0. What was it, 6? Just repeating sixes. Divided 37.5 times 0.1. 1/15th, yeah. 0.06. We have 3 sig figs, but I'm going to carry one extra digit here. And so quadruple 6. And then we're going to do the sodium hydroxide. The sodium hydroxide is going to be 12.5. So half as much of a dilution factor. Concentration of the original is the same. So this is going to be 0.0333 molar. I never round these. I just carry an extra digit. Avoid rounding. Because let's start. Now we have the reaction mixture. So this is the reaction mixture. And this is what we start with here in step 1. Now, we have a strong acid and a strong base. So the obvious reaction to the strongest acid plus the strongest base is hydroxide. This is the sodium chloride on water. So we have an initial from the reaction mixture. 8 cells in excess, 0.06. And then we have the sodium hydroxide, which is 0.0333. Then we have sodium chloride, which is going to be 0 molar, and H2O, which is just a liquid. Now, what is K for this reaction? Well, if I take a strong acid like HCl and react it with water, which is a very weak base, K is very large. If I take a strong acid like HCl and react it with a weak base, like acetic acid, K is very, very large. If I take a strong acid and react it with a strong base, like this one, I call K very, very, very large. So this reaction is going to go to completion, but we have to look at what the limiting reagent is. What is the limiting reagent here? HCl sodium hydroxide. It's going to be the sodium hydroxide, which is going to go to 0. So we're going to lose all of the limiting reagent. Once that's gone, no more reaction happens. So this is going to be minus 0.0333 on both sides here. What this is going to leave with is 0.0333 molar HCl left over. And my sodium chloride is going to be 0.0333 molar here. And then I look at what's left over. What's left over is this is an acid and it's conjugate base. So if we have an acid and it's conjugate base, then what type of solution is that? This is a conjugate pair. What type of solution is that?
Like a common ion solution?
It's a common ion solution. But if it's a base pair, then we call it a
Henderson Hasselbalch?
would be a Henderson-Hasselbalch buffer, but this doesn't qualify as a Henderson-Hasselbalch buffer. Why? This is not a Henderson, this is not an HH buffer. It's not an HH buffer. There's a couple of reasons for this. One is this acid is strong. This base is so weak we call it neutral. Henderson-Hasselbalch requires both the acid and the base to be weak. Yeah. And so it's not Henderson-Hasselbalch because it's strong and neutral. Sodium chloride is not a very good base. It's too weak. So essentially what we do is, yes, this is the conjugate base, but it's too weak. This is also common ion, but common ion requires initial amount here. So we don't call this common ion. If this is not zero, then common ion. But since this is zero, it's not really a common ion type scenario. But here, this could be a common ion. Okay, now this is a common ion mixture. So we could go to the next step and say, okay, this is a common ion mixture. But it's a strong acid. Normally, when we have common ion, what happens with a common ion type problem is that the common ion inhibits hydrolysis or reaction. And so when we have a strong acid, the common ion has no effect on hydrolysis. That's weird. So anyway, what we're going to do here is this, as we'll see down here, because that makes the next logical step 2. Step 2 is going to be, what do we have? We have an acid and a neutral salt for the common ion. And so in this case, we're going to say the acid is going to react with a strong base. Well, we've consumed all the sodium hydroxide. And so now the strongest base that's left over is just water. And so this is going to form hydronium and chloride. So initially, we have a 0 point. We're going to bring this down. So this is going to be brought down to step 2. I'm going to skip the sodium chloride ionization. That's complete. And then strong hydroxide salt, strong. And so this is going to give us 0.033. Now, typically, if we have a lot of product here to begin with, we don't expect as much change. But, the reason there's going to be no impact here is because K is equal to what?
Very low.
Very low. When K is large like this, then there's going to be no impact. This is a one-way reaction. And so I shouldn't even do this here. I shouldn't draw two arrows there. I should just draw this as one plate. It doesn't matter how much chloride I dump in there, it's not going to reverse this. And so the limiting reagent here is going to be HCl. We're going to have plenty of water. And so that's going to be 0. And it's going to go to 0.03333 mole. And then we're going to add another. So we're going to have 0.0666 mole. So in a typical common ion problem, having a long product here means the change is going to be reduced in the forward direction. If we're just interested in pH, stop here. Because this at this time, this is concentration of 10 to the minus 2. The most hydronium we're going to get from water would be 10 to the minus 7, and that's if there's nothing there, because common ion is going to impact water's hydrolysis greatly. We're going to get a lot less. And so let's go on to step 3 here and look at how much additional hydronium we get from water. And so some people might say, okay, we're going to get another 10 to the minus 7 molar, because that's the concentration of hydronium in pure water. But due to the common ion effect, we're going to get a lot less. And so this would be a common ion type problem. Yeah. And so the amount of hydrolysis that is plus X and plus X here is going to be a lot less. We don't need a lot to get our ratio. And Kw is going to be equal to the hydronium times the hydroxide. Here we're going to just use a simplifying assumption. I mean, Kw is so small. And then solve for X. So X is going to be Kw divided by 0.0 quadruple 3. Kw is 1 times 10 to the negative 14 divided by 0.0 quadruple 3. X is 3.0003. So we could just, when we do the percent change for these extreme cases, the percent change we can just do by order of magnitude. 10 to the minus 2 on the top, 10 to the minus OX on the bottom. 10 to the minus 13, which is the change on the top, over 10 to the minus 2 on the bottom, times 10 squared percent. So this is going to be 10 to the minus 13%. 10 to the minus 13%. This is 13 than 5%. So the simplifying assumption was fine. No reason to use it. So did we get much hydronium? No, we got 10 to the minus 13. In pure water, we could get up to 10 to the minus 7. But because of the common ion effect, we got 6 orders, a million times less hydronium. because of the common ion effect. And so it's 0.0333 plus, I'm going to write 12 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then a few. 5, 6, 7, 8, 9, 10, 11, 12, 3. And this is the PW is just a constant phase. So let's check our K here. Times 0.0333. And then I put 2 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. It's coming right on when it comes to negative 14. That's good. So you can see here that KW is not a significant contributor to hydrogen. We have a lot of hydrogen. This doesn't seem like very much hydrogen. 10 minus 2. Not that much. So let's go ahead and calculate the pH. Since we went all the way down here, we'll calculate the pH based on this hydrogen concentration. So let me go ahead and do that. It's going to be negative log 0. So that's 3, 7 zeros. 1.477. Three, so I'm going to go 1.477. 1. Negative 1.477. This is the missing pH. That's the pH, and then if I want the inventory, I just follow the steps down to see what the inventory is. So I'll just do that. The sodium I lost kind of track of sodium. I probably shouldn't be doing the hydronium is going to be the modest. Hydronium ion concentration is here, the hydroxide ion concentration is here, the chloride ion concentration is here. Sodium ion concentration should be the same. And that's it. Oh, no, sodium ion concentration is going to be less. Even that, neutralize. We have some unreactive. Only neutralize half of it. Okay. We can go to the equivalence point next, 25 milliliters. But at the equivalence point, I add just enough to neutralize everything. And so we can figure out what the concentration of the sodium chloride is at the equivalence point. And so here the pH is 1.477. We'll go to the equivalence point and then try that. If you do millimoles and we're adding 25.0 milliliter of sodium hydroxide. When we do that, we're going to end up with a total of 50 milliliters of mixture. And HCl is going to be a 25 to 50 dilution. 3 6 It's going to give us 0.0500 molar. And then the sodium hydroxide will be the same dilution factor, 25 to 50, gives us 0.0500 molar. So we go ahead and do, this is our step 5. Preliminary step. Now step 1, we take the strongest acid, HCl, this is strongest base, sodium hydroxide, and the form of sodium chloride. Very, very, very low. Neutral here is 0.0500, 0.0500. Was it 0.0? No, 0.100, so 0.0500. So this is stoichiometric, so you can eliminate the region. You have equal amounts, and this is going to come out 0.500. To keep track of the inventory, you may want to do this. The sodium chloride is a strong electrolyte, so it dissociates into sodium chloride. I don't know if we want to call this an official step, but I'll call it step 2 here, using 0.0500. So we can say 0, 0. And so this is going to go to completion. So we're left with 0.0500 more sodium ions and 0.0500 more chloride. Okay, now we look, since there are different strategies you use here. The general overriding one is just you take the strongest acid plus the strongest base for each step. But it depends if if you have a base solution, then you pick the strongest base plus water. But if you have an acid solution, this is needed. The sodium ions aren't acidic and chlorine ions are too weak to be basic. And so we pick the strongest acid present. What would the strongest acid present be? We ran out of HCl from step 1, and we ran out of sodium hydroxide. Water. The strongest acid will be water. The strongest base? Water. Water is the strongest base in chloride. Now here there's no common ion effect because we're starting off with 0 and 0. None of the previous steps contributed to any of these ions here. And if that's the case, then this is just going to be plus X, and we're going to get X molar and X molar. And then we have KW is equal to 1.0 times 10 minus 14, which is going to equal X squared, and therefore X is equal to 1.0 times 10 minus 7. This is the most hydronium we're going to get. And there's no common ion effect. This is just pure water. If there's common ion effect, then we're going to get less. We're going to get less, but overall we could have more. We're going to get less hydrolysis. It doesn't matter if the common ion is hydronium or hydroxide, we're going to get less hydrolysis. But overall, we could end up with more hydronium in an acid solution. We have a lot of initial acid there, so that would be more overall. In a base solution, we have a lot of initial hydroxide, and then a bit more. But in terms of water colliding with water to produce hydronium and hydroxide, this is going to be the most. And so what this does is it gives us an idea of when we need to worry about KW. We need to worry about KWs when the concentrations are very low. Like if my concentration were 10 to minus 7 molar initial hydronium, then I worry about Again, this is about the same order. 10 to the minus 8, 10 to the minus 9. If it were 10 to the minus 6, I probably wouldn't worry about it. But 10 to the minus 7, 10 to the minus 8, 10 to the minus 9, and smaller, I'm going to worry about it. KW should be significant, absolutely. Anyway, the pH here, this is 2 sig phase, so the pH is going to be 7.00. Now this is at 25 degrees C. And so the pH meters, the old style pH meters, when you look at an old pH meter, there used to be a little knob here, which is a temperature control knob. What happens is, as the temperature goes above 25 degrees C, you get more violent and more frequent collisions, which generates more hydrogen. And so at higher temperatures, we get more hydrogen. At lower temperatures, we get less hydrogen. And so the pH changes with temperature. Higher temperatures means that the curve, what was the name of this curve? Put the population on the y-axis and the energy on the x-axis.
And Maxwell-Boltzmann.
The Maxwell-Boltzmann curve shifts. And so at lower temperatures, at higher temperatures, it shifts. There's a certain minimum energy required for reaction. And so at higher temperatures, you have a greater population. At lower temperatures, you have a smaller population. And so at higher temperatures, we get more reaction, which generates more hydronium, which the more hydronium, the lower the pH. So pure water at higher temperatures has a pH less than 7. And at temperatures more than 25, has a pH greater than 7. Isn't that's a headache, because is the lab temp the same every day? No, the lab temp changes. So do you need to do a calculation using the Maxwell-Boltzmann distribution to figure out what the pH is going to be for each day for pure water? Or have a sample of pure water. Do you want to do that every day? Oh, the temperature is 24. I'm going to recalculate my pH for pure water. Nobody wants to do that. Everybody wants water to be pH 7 regardless of what the temperature is. And so do you know how they do it? They have a little knob there. So if the temperature is off, they just adjust the knob until it goes back to 7. And so what they do is they just normalize it so that water is always pH 7 regardless of what the temperature is. We used to have to do that manually, doing this. But with electronics nowadays and thermocouples and temperature probes, the pH meters can do this automatically. So we don't have to hassle with this anymore. It used to be a bit of a hassle. So the pH at the pure water is 7 at 25 degrees C. Other temperatures, we're still going to call it 7, but it's going to have to be adjusted electronically. Does that make sense? Otherwise, you're going to have to memorize the pH of water at multiple temperatures, which you wouldn't want to do.
Would that mean that all the ionization reaction is endothermic?
Yeah. It's endothermic because we're breaking bonds. Although, we're also forming bonds, but it's endothermic because we're going up in energy. Because this is a very weak base. This is a very weak acid. And this is going to be a stronger, much more stronger. In fact, it is a strong acid, and this is a strong base. And so in this case, we're going up in energy. This is why, K is so small. 10 to the minus 14, it heavily favors the downhill direction. This is highly endothermic. And so at higher temperatures, you're going to populate this state more. At lower temperatures, you aren't going to have enough high energy molecules to make it up. And so decreasing the energy is going to keep falling. This part of the reaction is called kinetics. It's a little bit more complicated. Because we have something, a barrier called the activation barrier. And so when you actually look at the energetics of this, it's like, sometimes it's like this. You've got a con and you do it all, and it's in return. All right, let's go to the 1.5 or the 3/2 equivalence point. This is plus 37.5. So we've already shot past the equivalence point. Now we're in the excess space region. This is 62.5 milliliters. Let's figure out it's still 25 milliliters. So each of these I start over. I don't do them in sequence, even though in the titration I'll start over for each one, right? Just do it in sequence. But for calculations, the easiest thing to do is not to rely on previous calculations. Just start from the beginning. So what's the dilution factor for HCl? Well, it's still 25. I'm starting from the beginning, but now I'm going to 62.5. 25 divided by 62.5. 0.0400. And the new concentration for NaOH, this is going to be 37.5 out of 62.5. Remove from 0.100. 37.5 divided by 62.5. 2600. All right, now what we're going to do is we're going to just do step one. Step one, take the strong acid HCl and the strong base NaOH. I'm sitting where I saw it. Initial HCl is 0.0400. Initial NaOH is 0.0600. The linear agent now is the acid. We'll see all of that. We'll do about 0.200. Okay, now we look at what's left over. And then we pick the strongest acid in the strongest base. What's left over. There's no more HCl. So the next strongest acid would be what? Water. And the strongest base would be what?
Sodium hydroxide?
Yeah. And so we could, we could do this. We could take our sodium hydroxide from sodium plus hydroxide. It's a strong electrolyte. So we start off with 200 and 0 and 0. We can end up with 0, 200. Okay, so strong electrolyte. This way we can kind of keep track of the sodium ions rather than having to happen. And if we're interested in inventory, so that's going to give me a step 3 I'll write over here. My step 3 is going to be, okay, the strongest acid water. The strongest base is going to be hydroxide. I don't consider sodium hydroxide the base. I consider sodium hydroxide sodium salt. Sodium salts are, I consider hydroxide the strongest base. And so hydroxide is the strongest base. What's the strongest acid? The strongest acid is water. So what does this form? Hydroxide and water forms water and hydroxide. So there's no change. If there's no change here, then the only thing left would be what? There's no real change there. The only thing left would be, well, the strongest base was hydroxide and the strongest acid was water. What's the next strongest base? Water. And so the only thing left would be Kw. Now, would you do Kw if you're only interested in pH? No, I would stop here. Because Kw is going to be such a small contributor. It's going to be such a small contributor because of the common ion effect. And so we start off with 0 here, and the common ion would be 0.0200 from the previous step, hydroxide. And so we're going to add that with X and then 0.0200 minus X or plus X. The simplifying assumption should work. Here. And so we can calculate our X, which is going to be Kw 1 times 10 to the negative 14. It's always a negligible contributor. But it gives us two options. We could calculate the pH from this. Or if we stopped here, we would calculate the pH from this, but we'd have to do two steps. First step would be calculating the pOH. pOH would be the negative. And so 1.69 is 3, so 1.698. That would be 368, and I'll carry one extra, 9. And then pH would be 14 minus 9, which would be 12.301. We should get the same pH here, because this is the hydronium. So the pH should equal the negative log of 5 times 10 to the negative 13. Let's see what it comes out to. So negative log of 5 times 10 to the negative 13. It comes out to 12.3010. So here we didn't, hydronium just came from autoionization of water. The hydroxide here, we could actually add the X. If we add the X, it's not going to change the hydroxide much. So we could have calculated pOH as well. Or pOH here, and then pH. And then here. So different options. Okay, so that would give us our inventory and pH for them. So for today, the titration that we did here, we talk about HA, which is going to be weak, plus NaOH, is going to be strong. we're going to try this titration. And here we're going to do at 0.100 molar. So we're going to start off with 25.0 milliliter, 0.100. So this is titrating the acid with strong base. So we add 0 milliliters of base, milliliters of sodium hydroxide. And this is just chapter 16. So we just do Ka, maybe Kw, most likely not Kw. Probably just Ka. It depends on the acid. So we'll do, let's see. So there are certain points we want to get. Where's the equivalence point going to be? The equivalence point is still going to be at 25. And so that will give me equal amounts of base and acid. However, the pH is not going to be 7. The pH is going to be greater than 7. At the equivalence point. And the reason the pH is going to be greater than 7 is because of this form. If I have my acetic acid and sodium hydroxide, it's going to form the salt. The salt is sodium acetate and water. So if I neutralize all my acid and all my base, I'm going to be left with sodium acetate. But sodium acetate is not a neutral salt. You know, acetate is a base. Since it's a base, the pH is going to be greater than 7 at the equivalence point because we form a basic solid. This is a weak acid, so the pH down here is going to be higher. Since we're starting off at a higher pH, like 2 to 3 or something like that, then the increase is not going to be as pronounced. But in a strong acid, strong base, this steep rise happens over about 6 pH units. For a weak one, it happens over 4 pH units. So it rises at this. So we could just do some calculations here. At 0 milliliters of NaH, this is a chapter 16 type, and the rest of chapter 17. So if we use 0 milliliters of NaOH, then we just have acetic acid. And so we're going to just do pH calculations right now. We're going to have acetic acid. We're not going to do inventory. This liquid's going to get hydronium and acetate. Ka for this, it's a weak acid, is 1.8 times 10 to the minus 5. Initial 0.100, water clear, 0 and 0. And so if we look over at 0.100 minus x is equal x squared minus x. And then we just go ahead and do some fun stuff. So this will be x squared over 0.100. It's going to give us an x squared. And so we're going to take 1.8 times 10 minus 5 times 0.1. And then take the square root of that answer. 0.341 times 10 minus 3. So we're only allowed 2 sig figs, so 1.34 times 10 minus 3. If we're only interested in the pH, well, that's the pH right there. That's hydronium. This is this is minus point, actually, let's just go ahead and do it here. This is minus x. And so this is going to be 0.100 minus point 0.0013. Let's give you this point 0.099659. So basically, 99.659% of this acid remains. Only 1.341% is reactive. And so this is percent change, the percent reaction is 1.341 times 10 to the minus 3 divided by 0.1 times 100%. This is 10 to the minus 1. That's 10 to the minus 10. So this is 1.34%. It's kind of big, but it's still less than 5%. As it gets bigger, like closer to 5, you might consider using quadratic instead. This is really fast for the quadratic. You know, some of the earlier percent changes were so small. I ran out of email here so that I could add more pages. Maybe I shouldn't have done that. It's probably going to crash on me. I didn't. Bad looking. When the percent change is like 10 to the minus 8%, then there's no reason to do quadratic. But when it starts to creep up, you might consider doing quadratic to get a more accurate answer. In this case, it would be pretty simple to solve for the quadratic. And so let's do that as an aside calculation here. If we decided to use a quadratic, it would be x squared plus 1.8 times 10 to the minus 5 x, and then 10 to the minus 1 times 10 to the minus 5 and 10 to the minus 6. So that would be minus 1.8 times 10 to the minus 6 equal to 0. I mean, it's quick if you have a quadratic solver, of course, which we do. Or I did have it up.
I have a question.
Mm-hmm.
For the test next week, is it on Tuesday or on Thursday?
I'm thinking it's going to be on Wednesday, our lab day. What lab do I have scheduled? I have to take a look at the lab. Okay, it'll be on Wednesday. Yeah, chapter 16. Or Tuesday. What's the preferred? Is it more comfortable in this room or more comfortable in the lab, or it doesn't matter? Wednesday? Okay. Yeah, so we'll leave it Wednesday then. That's 1.33 2. Um, 1.3232 versus 1.341. So 1.33% versus 1.34%. It's small, but this would be more accurate. That's if the math is easy and you can do it quickly. And there's no reason to do this. But anyway, going back to this here, should we worry about KW? And so the hydronium ion concentration is 0.0013 4%. We're only allowed 2 C6, okay, not percent more. Should we worry about KW? What's the most you're going to get from KW? Well, give me a number over magnitude.
10 to the -7.
10 to the -7, but likely it's going to be much less because of the common ion effect. Will even 10 to the -7 have any impact on this? This is 1, 2, 3, 4, 5, 6, 7's out here. There's no impact. And so I wouldn't even worry about KW here. And so we're just going to go ahead and calculate pH based on this. So if I do using the one from the simplifying assumption, I get negative log 0.00134, which gives us a pH of 187, and I'm allowed two sig here. So 1.87, and I'll carry one extra digit. Okay? If I do the pH based on the quadratic that we just did here, what would I have gotten? Yeah. So this would be negative log of 0.001332. Let me do that again. Negative log of 1.332 times 10 to the negative 3.87. You guys screw that up? It should be 2.872, I think. It should be 2.875. So this is going to come out to 287. This is going to come out to 288. This is a slight difference. 288 would be more accurate. So it depends, it depends on how difficult it is to do that. All right, the next calculation would be, let's do the half equivalence point. So why don't you try doing the half equivalence point calculation? Are you going to do it? You don't need to do this on screen. doing calculation, titration calculation. Weak acid plus strong base, the half equivalence point. I did my step I, which is a solution solution. What's that? In step one here. And then this is the Ka for acetic acid. No, you don't have to know. It's there on the chart. I just rounded it. It's 1.76 times 10 to the minus 5 on our chart. I don't know how old that data is. In our book, it's 1.8 times 10 minus 5. So I'm just going to use the book's value. So, did you guys get some? Let me talk about this here. So you did the solution dilution. The dilution factor is the same as the last, so just reuse those here. And then you pick the strongest acid, acetic, with the strongest base, sodium hydroxide. Limiting reagent, sodium hydroxide. And then we end up with a product mixture that's going to consist of unreacted acetic acid and sodium acetate. And then you should recognize this. This is a weak acid and its conjugate base. Therefore, it's a Henderson-Hasselbalch buffer, HH buffer. And so the product solution, the product mixture is a buffer. In fact, this is how you can make a buffer pretty easily. You can make a buffer pretty easily by partially neutralizing the acetic acid. When you partially neutralize the acetic acid, it forms the product conjugate base here, and we have leftover acetic acid, so we can get a weak acid, weak base mixture. This weak acid, weak base mixture turns out to be a one-to-one mixture. When we have a one-to-one mixture, the ratio between base to acid here is 1, and log base 10 of 1 is just 0. And so the pH is just equal to pKa. We ever look up the pKa in a chart, or we calculate the pKa using the Ka here? And so that would be 4.74. We go back to our titration curve. We calculated the initial pH was 2.87. And so in the titration curve, we start off close to 3, 2.87. And then by the time we get to 12.5, here, we calculate the pH of 4.74. Now, pH stays relatively flat in the buffer region here. So, how flat does the pH stay? You know, I don't know. I have it kind of slow. You know, how flat is this? And so we call this the buffer region. The buffer region is going to extend from the initial here all the way to the equivalence point, just about there. And so this is the buffer region. Now, over here, the Henderson-Hasselbalch is not going to work as good because the Henderson-Hasselbalch requires a simplifying assumption to be correct. And so we probably don't want to use the HH equation here. We should probably use ice for step 2. And maybe right at the beginning, use ice. But in this, we'll call it maybe the green zone here in the HH equation is pretty good. So we can use the HH equation over a pretty wide range. And the advantage of using the HH equation is that we can skip the ice table. So that's exactly what I did here. Rather than having B here, we skip that. The reason we would have gone to a K or KB is because we probably would have done this. If we were thinking about ice instead, we probably would have gone to a step 2, which is the strongest acid present. The strongest acid present would have been HAC. And the strongest base present would have been acetate. But what happens when HAC and acetate react? What do we form? Yeah, acetate and HAC. Doesn't no change. Then, okay, what we'll have to do is we'll have to, instead of doing this as our step 2, we have to pick the strongest acid in the next strongest base. So the strongest acid, let's say, is HAC. The next strongest base would be H2O liquid. And this one works. This will form hydronium and acetate. Or you would have picked acetate as being the strongest base, and the next strongest acid after acidic would be H2O. And what would this form? HAC and hydroxide. And so which one should we do? Should we do the first one here? Or should we do the second one here? Or do we need to do both? I think you could use one of them to get the other. Yeah, actually, these describe the same. These are equal. And so do one or the other, not both. That's if we wanted to do the ice. And so we would have done that. It's very rare that we have to do it the ice way in the buffer region. It's only at the very extreme. This is like less than a drop away from the equivalence point. Right? So if you're like less than a drop away from the equivalence point, then you might have to use the ice. This happens in about 1 drop right here. No, way up here. From down here. Otherwise, we'll just use the Henderson-Hasselbalch. And so what that means is that there's a way to shortcut these calculations. And so buffer region shortcut. So for the buffer region shortcut, we can go from equivalence points, X equivalence points, to pH easily. So let me show you how we do that. So that region is going to occur from 0 to 25. Different problems, it might go to 50, it might go to 30, it depends on the numbers. But for us, it's from 0 to 25. And so this is called the equivalence point here. And then there are going to be quick calculations. The half equivalence point is very fast. You don't even have to do this. If I gave the half equivalence point on a test, you just say, oh, the pH is equal to pKa. This is standard, so you can skip all that. So it wasn't even necessary. And so this is acceptable, no work necessary. pH is equal to pKa. No work is necessary because everybody should know that the pH is equal to pKa at the half equivalence point for weak acid, strong base. If you don't want to do that, you can do the calculation. Now the other equivalence points are very fast. So let's look at the 1/4 equivalence point. The 1/4 equivalence point is going to occur at how many milliliters? 6.25. So, are you good? So, you here or computer? I was going to move to the computer, but I'm running out of time. So we know we're in the buffer region. And we know we're at the 1/4 equivalence. So pH is going to equal to pKa plus the log. This is going to be the log of, okay, how much product am I going to form? I'm going to form 1/4 because I've neutralized 1/4 of it. And how much reactant am I going to have left over? I'm going to have 3/4 left over. And so this is the way we think about this. The way we think about this is that I have my HAC plus NaOH. And if I start off with 4/4 here, and I neutralize 1/4 here, then how much NaHC will I form? H2O being a liquid here, NaHC 0. So we're going to lose 1/4 of this, and we're going to lose 1/4, and we're going to gain 1/4 here. So what we're going to end up with is we're going to end up with 3/4 left over and 1/4 of product conjugate base at the end. And so this is where I got this. I throw this in up here, that's my base. I throw this in down here, that's my acid. And so this is going to equal the pKa plus the log of 1/3. This is log of 1/3. Do you know what the log of 1/3 is? It's minus 0.677. So this is the pKa minus 0.677, if I recall. No, I better double check that because it's been a while. Log of 1 divided by 477. Negative 477. Yeah, it's been a while. I've done that. .477. So I go up here and I just do this. This is 474, and I just go, okay, I'm going to subtract 0.477 from that. 474, 4. I get 4.266. Oh, just round that. 4.266. So at the 1/4 equivalence point, the pH should be 4.266. Okay, do you know what it's going to be at the 3/4? At the 3/4, I'm going to add 477 to that. And so 4.74 plus 0.477, and that gives me 5.217. Let me just get 5.22. This will be 4.27. How did I get to 3/4? 3/4 is very quick because it's this flip. So the way I visualize it like this, you know, the way I visualize it is I'm going to have my HAC and my NaOH, and what I'm going to do is I'm going to neutralize 3/4. So I have 3/4, and my NaC is going to be minus 3/4, minus 3/4. So I'm going to be left over with 1/4, 1/4, or 3/4. So when I look at the Henderson-Hasselbalch, the pH is equal to pKa plus the log of 3/4 over 1/4, which is the log of 3 over 1. And so this is inverted, which is plus 0.477, plus 0.477. So the log of 1/3, I kind of sort of have memorized, and log of 3, which is inverted. There's one other one I have memorized, and this is easy. The 1/10 and the 9/10 equivalence points. So I like to do the 1/10 and the 9/10 equivalence points. Okay, the 1/10 equivalence point is going to come at how many milliliters? And so it's going to be 1/10 of 25. And so this is going to come at 2.5 milliliters. And then I'm going to go to 9/10 of 25. 9/10 should be 22.5 milliliters. And so I could get those very quickly. Because the pH at the 1/10 equivalence point is going to be like this. At the 1/10 equivalence point, I'm not even going to bother with the ice table. I'm just going to look at the Henderson-Hasselbalch. The pH is equal to pKa plus the log. And the product, well, how much product have I formed? I formed 1/10. How much do I have unreacted? 9/10. You see that? Why do I like the 1/10 and the 9/10 equivalence points? Actually, I don't. This one's not so great. This is equal to the pKa plus the log of 1/9. I don't like that so much. Even though calculating the volume is quite convenient, I don't like this one that much. You know which one I like more? I mean, this one's not bad. Let me tell you which one I like more. I like the 1/11 equivalence point a lot more. Now, where does the 1/11th equivalence point come in? So if 25 milliliters, we call that 11/11th equivalence point. So if 25 milliliters is the 11/11th equivalence point, then what is the 1/11th equivalence point? Where is that going to come in? And so the 1/11th equivalence point is going to come in at 1/11 of 25 milliliters. What is 1/11 of 25? So this is 25 divided by 11, and it's going to be 2.272 milliliters. I like this. And so I want to figure out the pH of 2.27 milliliters. Figure out the pH of the 1/11th equivalence point is very easy because this is it. The pH is equal to pKa plus the log. Okay, how much reacted? 1/11th reacted. How much do I have left over? I have left over 10/11 left over. Does this make sense? And so the reason I like the 1/11th equivalence point so much is because of this. It's equal to pKa plus the log of 1/10. Well, what's the log of 1/10? The log of 1/10 is minus 1. So it's pKa minus 1. So it's very quick to get this. The pKa was 4744, and so minus 1, this pH is going to be 374. It'll be the pH. And the 10/11th is very nice too. At the 10/11th equivalence point, well, what is 10/11ths of 25? So 25 times 10 divided by 11 is going to give me 22.72 milliliters. So at 22.72 milliliters, the pH is very easy to determine because at the 10/11th equivalence point, then the pH is equal to pKa plus the log of, okay, 10/11ths has been converted into base. That means I only have 1/11th reactant left over. And so this is pKa plus the log of 10, which is 1. And so this is pKa plus 1. And so at the 10/11th, it was 474. I'm going to go up to 574. And so from 2.27 milliliters to 22.7 milliliters, I'm going to go from 374 to 574. I'm going to go up by 1 pH unit, 2 pH units, 2 pH units. Does that make sense? And so these I get mapped quickly. So I do that. I might do the quarters, minus 0.477 plus 0.477. So I could get 5 points in the buffer region without spending much time. These are very quick calculations. Oh, I'm out of time. All right. Well, we're going to continue with the computer stuff next time, or one of these times.